In this video, we'll discuss how do we identify the local extreme values, right? Let's try to do that in this picture here. So by looking at the graph, so this blue curve is a function given by y equal to f of x. And by looking at the blue curve, we can identify some three local extreme values, right? At this point here is a local maximum, right? Because if you have any number, let's say less than 0, right? And so that function value is the biggest, right? You have a small neighborhood, y, x. You can see that function value here is a local minimum value, right? You can see that you can get, this is actually also the absolute minimum value, right? And here, this is a local max, but also this is also the absolute max, right? Now you can see that whenever you have a local max or local mean, and sometimes you do have a absolute maximum, absolute mean, right? Inside A, B, not at A or B, inside A, B. So the tangent line is always horizontal, right? But not hard to imagine that if your tangent line is going up or going down, this cannot be a local extreme value. It's getting larger and larger or smaller and smaller, right? So now you can see that this is one of the conditions. By looking at the derivative, we can identify local extreme values, right? So this is support proved by one of the very famous mathematician theorem. This is called Fermat theorem. A very long time ago, right? So if f has a local extreme value, maximum or minimum value at C, right? F of C is either local maximum or local minimum. And f prime of C exists. So the function due to C, and also which means the slope exists, right? Slope of tangent line exists. And only one thing could happen by our discussion, right? Then what happens is f of C equal to 0, right? Very nice result. So this gave you a way, then f prime of C is 0. This gave you a way to identify the local maximum and local minimum if the derivative exists, right? But what if the derivative doesn't exist? We just include it, right? So let's write down a definition here, motivated by this result. Definition. A critical number of f, right, is a number C in the domain of f such that either we have f prime of C equal to 0, so that's a possible local maximum or local minimum, right? Or f prime of C does not exist. So f prime of C equal to 0 doesn't imply you always have a local extreme value, either positive or negative. There are counterexamples, but that's a necessary condition, right? So we just look for all the numbers such that f prime of c is 0, and also f prime of c does not exist. So that's all the possible places you get local maximum or local minimum value. Then among them, you will get your extreme values, right? So that is basically the motivation behind this definition. Let's see a quick example here, right? Quick example. And we want to find the critical numbers. So critical numbers, remember, these are the numbers at which the function might reach absolute or local maximum or minimum, right? The following function. And we have a g of x equal to the third root of 4 minus x squared, right? No, third root, right? Now you can see that the function here, because critical numbers must be a number in the domain, right? So before you figure out the critical number, you should get the domain of this function. This is third root, evens root, so which means you can plug in positive number or negative number. It doesn't matter, because the third root of a negative number always exists, right? So the domain of G here is all real numbers, right? This is from negative infinity to positive infinity. So whichever number make the derivative to be 0 or make the derivative doesn't exist, then this number will be a critical number, right? Now, how do we do that? Because no matter which, you are looking for derivatives. Let's try to differentiate our function. G prime of x is equal to, again, chain rule here, which is 1/3 4 minus x squared to the power -2/3 times -2x, right? So in this case, let's try to write, we don't like negative exponent. Let's rewrite everything in a form of positive exponent, right? So this is negative coming from here, -2x, that's our fraction, that's our numerator, and 4 minus x squared to the power 2/3, right? Change the negative exponent to the denominator, right? Now, okay, we are looking for the c's, right? Such that either g prime of c doesn't exist, right? All g prime of c equal to 0, right? So you have a fraction. So the fraction is 0 when the numerator is 0, right? The fraction does not exist when the denominator equal to 0, right? So we write that down here. Note g prime of x equal to 0 when 2x is 0, which is a numerator, and g prime of x does not exist when denominator, which is 3 times 4 minus x squared to the power 2/3 is 0, right? So this is our denominator. So a fraction is 0 when the numerator is 0 and denominator, right? And does not exist when the denominator equal to 0. So using our observation, right? Hence, g prime of x equal to 0 when x is 0, because 2x is 0 when x is 0, right? G prime of x does not exist when what happens when x is either 2 or -2, right? You can solve for this equation here, right? Take divide by 3 first, then raise to the power 3/2. You get 4 minus x greater equal 0, which means x is either 2 or -2. So we have the critical numbers of G are what? 0 to -2, right? So that's our final answer for this problem. And so that's it.